Hello everyone, I'm Andreas and I'm going to present our work, Policy Engage Fallback Nodes in Behavior Trees. Behavior trees have become extremely useful and popular in robotics because of their numerous advantages, including modularity, reactivity, hierarchical decision making, and being equal expressive as finite state machines. We have identified that behavior trees rely on static ordering for managing failures and uncertainties. However, this fixed approach fails when contexts change in real time as it lacks the flexibility required to adapt. We also identified that when we're coding context-sensitive decisions in behavior trees, the trees tend to be larger and more complex, and fallback nodes can be seen as crucial decision points, and some extension of behavior trees have attempted to introduce adaptability to them. However, the decision-making process should be understood and trusted by humans, and current solutions do not offer any way to do that. In our attempt to improve human-robot interaction, we wanted to extend behavior tree structure to adapt to the environment by reasoning about the appropriate action, build a meta model to humans how the robot acts in different situations, and give the freedom to humans to extend and modify the robot's policies. To dive in our extension, we have three main components: the reasoning system, the policy engage fallback node, and an interface for user guides. The reasoning system relies on prudent and declarative AI programming language, which is compatible with machine coaching, a human-in-the-loop machine learning approach. For the policy engage fallback node, we modify the original fallback node to reorder children based on the inferences of the reasoning system. And finally, the interface for user guides aim to let humans to modify the policies. However, currently in our proof of concept, users can only add, remove, or modify rules. The engage fallback node uses fluence as what the robot can observe in status and environment, action as what can be done, and the policy as rule for guiding the decision-making process to infer constraints about the ordering. This partial ordering, based on the constraints, reorders the children of the fallback node to prioritize certain children over other children. We design an experiment aimed at conducting a qualitative study. We develop a custom mini-grid environment of an empty room with moving obstacles. The obstacles differ by their color, and every obstacle based on the color has a different probability to move in the next moment. The goal of the agent was to reach the target goal, marked as green, without colliding with any obstacle and minimize the steps. Our solutions are based on a traditional behavior tree, a behavior tree with utility-based fallback nodes, and a behavior tree with policy-based fallback nodes. And here is a demonstration of our policy-based solution. Fluents include whether there are any obstacle in the next step and which alternative path, left or right, is closer. The rules are structured to ensure that waiting is more advantageous when obstacles are more likely to move, and turning is prioritized based on the shortest distance to the goal. We also demonstrate to the participants the ability to modify the agent's behavior by changing the policy as they want. Based on the experiment, we developed a questionnaire aimed at exploring adaptability, transparency, and trust in the different approaches. Our results include that adaptiveness to the fallback node is perceived crucial, the incorporation of user guidance is a desired addition, our approach is perceived as more transparent and explainable to other approaches, and is more adaptable to changes in requirements. Non-experts could potentially assist in the decision-making process. And finally, the ability of the agent to explain the action policy and for humans to modify it seen to positively affect their trust towards the system. For future work, we want to develop an interface for humans to understand and modify action policies in human-robot interaction scenarios. We could also compare trained action policies with probabilistic solutions to evaluate the benefits of each approach. Here are a few benefits that our extension potentially brings to the behavior tree structure.